Hi guys, I'm live. It's boring time. It's time to do a math lesson. I'm sorry, but it's part of life. It's part of what can be learned or known, and it's part of what I've studied in my life. So it's part of me, whether I like it or not, or maybe doesn't say I didn't like it, but whether I like it or not, it's still a part of me. So I'd like to do some math lesson if that's okay. How you guys doing? Peace. Okay. In calculus, uh, let's you have some functions that are common, like you have the exponential function, y equals e to the x, and you can find how do they do this. I'm trying to remember. You can prove that the derivative of e to the x, or y prime, equals dy dx equals e to the x. So e to the x is a function, or maybe even the only function, but it is at least a function, the function where the derivative of the function is equal to the function itself. Let's look at this for a second. I have these propped against my CDs and I don't want to knock them over, so I'm writing kind of lightly. I probably shouldn't prop them that carelessly, but I did. Hey, maybe I know. Okay, so if you have a function, let's plot e to the x. This is y, this is x. E to the x looks something like this. It looks like this. Something like that. It's like a curve that gets higher and higher, faster and faster. I shouldn't really make it on the x-axis because it really isn't on it. It's always above it, even if only by a very small amount. Epsilon, you could call it. Okay, look, that's not a very good drawing of it. We'll do a little better job. Like that. Yeah. Okay, it's still not a very good drawing, but then again, I'm not an artist. I'm not a drawing artist. Let's test it. The dy dx is the rise over run, or the slope of the line, or the curve at any given point. It's literally why it's dy over x. Dy would be a little y part, and dx is a little x part. So dy dx literally looks like a small instantaneous derivative just by looking at it. And that's a point that a lot of calculus teachers don't bring out, but I think they should. Bring out the little things, let the cool little thing like that can be interesting, a good way to remember stuff. So if x equals negative infinity, so very, 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 very high negative number, e to the x equals e to the minus infinity equals 1 over e to the infinity equals 0. So as you can see, the derivative, the slope of the function is at x equals negative infinity is 0. It's only going, it's not going up at all or down. It's going, it approaches going up nothing, but yet going across by something. So the slope becomes dy dx becomes 0 over dx, and that's 0. As you can see, slope is 0, like a horizontal line. Cute little catch there, and actually it was a miss, not a catch. Okay, so far so good. So far that's consistent. I am going to try to make this an interesting video before I'm done. Let's see if I accomplish that. How about at x equals 0? At x equals 0, the derivative dy dx equals e to the 0, which is 1, and as you can see, that's about right. The dy is about the same as the dx because it's about 1 to 1. The slope is about 1 over 1, which is 1. So that looks about right. And then when x equals infinity, then e to the x equals e to the infinity equals infinity. And as you can see, this slope goes up to where it becomes straight up. And that's infinite, or at least some rise with no run, and maybe 1 over 0, which is infinity. So, right? So that checks out so far. That all looks good. But I'm not done. I'm not done yet. Can I be? Okay. Just mark my hand. No, I missed. Okay, now let's do some more fun, more work here, more fun stuff. Hopefully I'll make you guys learn something from this video. There's another function called log of x, y equals log of x, a natural logarithm. That's why there's an n. Natural logarithm is base e logarithm. So the natural logarithm is defined such that the logarithm of x equals if y equals logarithm of x, then that is defined such that e to the y equals x. In other words, the logarithm and the exponential are inverse function, are inverse operations. So the logarithm of e to the x equals x, and e to the logarithm of x equals x. They reverse each other. Logarithm e to the x is x, e to the logarithm of x is x. So if I have y equals e to the x, then I could take the logarithm of both sides, natural logarithm, I could get logarithm of y equals x. So I could say x equals the logarithm of y. And that's if y equals logarithm of x. I mean, y equals e to the x. And then if I want to figure out the derivative of logarithm of x, I made this little trick myself. I'm highly certain I'm not the only one that's thought of it, but I did think of it myself, and I've never seen it in a book, but this is my idea. We say y equals e to the x, logarithm of y equals x. Then you have x equals logarithm y. And then you have d. Oh no, let's do it a different way. I don't always do anything. Nobody always does anything, because one day you won't live. And you're living right now, so you won't always live. If y equals e to the x, then logarithm of y equals x, because the logarithm and e are inverse functions. That means x equals logarithm y. That means d y equals d to the x, logarithm y equals logarithm of x. Am I goofing here? Oh yeah, I am. That was a goof. Let's try it again. I don't rehearse for this. I just get a feeling I want to do it. Y equals logarithm of x. So that's what you want the derivative. Okay, so that means e to the y equals x. Okay, that means x equals e to the y. And we know that from the fact that the derivative of e to the something is e to the something, that dx dy equals e to the y. And we know dx, yeah. But we want to know the derivative of logarithm of x. If y equals logarithm, if we want to know, if y equals logarithm of x, we want dy dx. But that's the reverse of dx, that's reciprocal of dx dy. So I can say dy dx equals 1 over e to the y. But e to the y is x, because x equals e to the y. So we have dy dx equals 1 over x. that shows that the derivative of the logarithm of x is 1 over x. And that proof is my own idea. I've never seen it in a book, and yet I figured it out. I'm sure 1,000 million other people have too. Just I haven't heard about it, and they haven't heard about me unless they watch this video, or others that I've said this in. So far we learned what the derivative of. Now we know what the derivative of the logarithm is. Logarithm of x. The derivative of the logarithm of x is 1 over x. They usually give a much harder way of doing it than the way I just suggested. The way I suggested works. Einstein said, things should be made as simple as possible, but not simpler. But it is possible for it to be this simple, so it should be this simple, I think. So let's see if this adds up. Let's do a y-x diagram again, xy. xy. The logarithm of x looks like this. I'm not sure how to explain it, but it just kind of goes like that. Goes like that. That's a log of y equals logarithm of x. That's cool because the y equals e to the x does something like this. So they mirror about the line about this line y equals x. Y equals x is a line of slope 1, straight line to the origin. You know, y equals mx plus b, mx plus b, slope intercept is 0, m is 1, so y equals x. It's a line going through the origin of slope 1. And the exponential function, e to the x, is a mirror image around this y equals x line of logarithm of x. Because they're inverse processes. A way of looking at that is if a point here is this point would be this. Well, that's still reflected around that axis, isn't it? If this point is dun, this one is would have to be 1 over x, y would have to be like this. It would have to be, this went forward, up, and up 1. This would have to be like that. And these points here are also reflected around y equals x. I just reversed the x and the y. If this is 3 and this is 1, whatever, this is the opposite of that, and you get the point that is reflective around this line, with the line being y equals x. That's a good way of looking at it. However, I hate to say however or but it's a word. Sometimes you have to say that. We're back to the y equals logarithm of x right now. So even though it's a beautiful, elegant thing I just drew, mathematically speaking, I'm erasing it and going back to just the simple logarithm, y equals logarithm of x, which I plotted here. But I like patterns in math things. Okay, so that's y equals logarithm of x. That's the line y equals x, but this is y equals logarithm of x. Well, let's check some things out. I said the dy dx equals 1 over x, didn't I? Proved it, in fact. Let's see if that adds up. This dy dx is the slope of this curve, which is logarithm of x. Let's see how that works. For x equals 0, dy dx is 1 over x. Dy dx, I'll write it. Dy dx equals 1 over x. Oh, well, x is 0. So dy dx equals 1 over 0, which is infinity. Any number divided by 0 is either positive or negative infinity. Don't say always infinity. If that were negative 1, it'd be negative infinity. X0, 1 was infinity. And sure enough, at x equals negative infinity, at x equals 0, dy dx is straight up, which is infinite slope, because it goes up a certain distance, rises with 0 run. 1 over 0 is infinity. So you can see that this slope is infinity at x equals 0. As x approaches 0, the slope of logarithm of x becomes positive infinity. Sure, checks out from the diagram. Then at x equals 1, you have y equals logarithm of x, dy dx equals 1 over x. At x equals 1, the derivative dy dx is 1 over 1 equals 1. And sure enough, that maps out to be about true, doesn't it? That's a parallel to this line, actually. It looks like if you go dy is, and then the dx are equal proportionately. So that's got a slope of about 1. Sure enough, at x equals 1, dy dx is 1 over x. And at x equals 1, 1 over x is 1 over 1, which is 1. And then at x equals positive infinity, x equals infinity, you have dy dx equals 1 over x equals 1 over infinity equals 0. And sure enough, this line starts going toward a 0 horizontal where it has 0 slope because it goes up 0, the dy, and the dx is something. And 0 over something that's positive is 0. It starts to go toward 0. You can see that from the graph. So I've never done this exact whole lesson in my life on any YouTube channel. In fact, I'm revisiting a lot of math in my head, and including simple stuff like calculus, even though calculus is not simple, but it's kind of on it's gateway math. It's like the pot of math. It's the gateway between basic math and higher math. Like marijuana is the gateway between alcohol and hard drugs. Calculus is the gateway between arithmetic and complex variables and all the higher math, quantum mechanics and Fourier transforms and systems engineering and all that. You got basic math, you got calculus in the middle, and then you got higher math on the other side. If you can get through calculus and you're still in rock and roll.